You've had a long day. Your mind is still buzzing with thoughts, but it's time to let them settle now. Tonight, allow your consciousness to drift gently through cosmic immensity while your body finds the rest it deserves. Close your eyes, breathe deeply, and let yourself be carried toward the edges of the universe. For generations, astronomers believed they had grasped the dimensions of the cosmos, a measurable expanse, stretching roughly 14 billion light-years in every direction, populated by a few 100 billion galaxies scattered through the darkness. This vision seemed vast, yet comprehensible, something the human mind could eventually wrap itself around. Then, the James Webb Space Telescope turned its golden mirrors toward what appeared to be absolute emptiness, and that certainty crumbled like stardust. Webb unveiled an observable universe extending nearly 93 billion light-years across, teeming with stars hidden where nothingness was supposed to reign. Fully formed galaxies emerged just 300 million years after the Big Bang, black holes growing faster than our equations predicted, structures far too massive for their supposed age. But the most unsettling revelation isn't how far Webb can see into the darkness. It's what these discoveries suggest about what exists beyond our cosmic horizon, and why the vast majority of the universe may remain forever beyond our reach. Let your breathing slow. Allow these thoughts to float through your awareness like clouds drifting across an evening sky. To truly grasp what the James Webb Space Telescope reveals, we must first abandon the notion that space is merely something we look across. In our universe, distance and time are inseparably woven together. Light moves at a constant velocity, approximately 186,000 miles per second. It's the fastest phenomenon that exists, swift enough to circle our planet more than 7 times in a single heartbeat. Yet even at this incredible speed, distance immediately transforms into delay. The farther light travels, the older the image it carries when it finally arrives at our eyes. When you observe something a mile away, you see it as it existed a few millionths of a second in the past. The moon you gaze upon shows you an image from 8 seconds ago. The sun you admire, you're not seeing it as it exists at this moment, but as it appeared 8 minutes earlier. The sky above us isn't a live broadcast of reality. It's a stream of information arriving late, an archive of moments already past. These delays are so infinitesimal that we never notice them in our daily existence. Our brains perceive the world as immediate and continuous, creating a seamless experience of the present moment. But as our gaze ventures farther outward into space, the delays expand, and eventually they reshape our entire understanding of the cosmos itself. The nearest star beyond our sun appears to us as it existed more than 4 years in the past. The center of our Milky Way galaxy reveals itself as it was 26,000 years ago. And when we peer beyond our galaxy into the vast expanses between stellar systems, we're no longer observing the universe as it exists today. We're reading earlier chapters of a story already billions of years old. The night sky, then, is not a snapshot of the present. It's an archive of cosmic history. Every point of light carries a timestamp. Every photon is a messenger from a different moment in the universe's long story. The more distant its source, the more ancient the message it delivers to us. Let yourself relax deeper. Feel the weight of your body sinking into comfort. The challenge lies in understanding that the universe doesn't preserve these messages unchanged. As the universe expands, space itself stretches outward, and when space stretches, it stretches the light traveling through it. Wavelengths grow longer, energetic blue and ultraviolet light shifts toward red, then slips into the infrared spectrum that our eyes cannot perceive. This phenomenon, known as redshift, isn't merely a visual alteration. It's a record indicating how much the universe has expanded since that light began its journey across the cosmos. Redshift acts like a cosmic clock, ticking away the eons. The more stretched the light appears, the longer it has been traveling, and the earlier in the universe's history it was originally emitted. For decades, astronomers relied on telescopes optimized for visible and ultraviolet light. That narrow slice of the electromagnetic spectrum human eyes evolved to detect. Instruments like the Hubble Space Telescope transformed our understanding of nearby galaxies, star-forming regions, and the large-scale structure of the cosmos we inhabit. But as scientists attempted to look farther back in time, the universe began to fade from view, not because it wasn't there, but because its light had changed beyond recognition. Ancient galaxies didn't disappear into nothingness. Their light simply drifted beyond the range those telescopes could detect. The James Webb Space Telescope was specifically designed to follow that missing light into the infrared realm. Its mirror spans more than 21 feet across and is coated with a microscopically thin layer of gold. Gold being chosen for its extraordinary efficiency in reflecting infrared wavelengths. Webb doesn't orbit Earth as Hubble does. Instead, it operates nearly 1 million miles away, at a stable gravitational point where it can remain steadily pointed, shielded from the heat and glare of both Earth and Sun. That distance allows Webb to stay extremely cold, and that cold is absolutely essential. Infrared light is closely tied to thermal radiation, and a warm telescope would drown out the faint signals it's attempting to detect. Webb had to become quiet enough to hear the universe whisper its oldest secrets. Year breathing is becoming slower now, deeper, more rhythmic. When Webb stares into a region of sky that appears completely black to our eyes, it isn't searching for emptiness. It's waiting patiently, waiting for photons that have been stretched almost to invisibility by billions of years of cosmic expansion. Those photons arrive slowly, sometimes individually, one at a time. Webb may observe the same patch of sky for many hours, even days, patiently collecting light that has crossed nearly the entire observable universe to reach us. And what it discovers there isn't a quiet, tentative cosmos just beginning to form its first structures. It finds a universe that's already remarkably busy and complex. Some of the galaxies Webb has detected formed when the universe was only about 300 million years old, less than 3% of its current age. To grasp how remarkably early this is, imagine compressing the entire history of the universe into a single calendar year. These galaxies would appear on January 2nd. According to long-established cosmological models, this era, often called cosmic dawn, should have been relatively dim and sparse. The first stars were expected to ignite slowly and reluctantly. Early galaxies were predicted to be small, fragile collections of gas and nascent stars, requiring hundreds of millions of years to grow into anything substantial. But Webb observed galaxies that were already bright, already massive, and already forming stars at intense rates comparable to much later cosmic epochs. Some were so luminous that even if they were located much farther away, Webb could still detect them. That brightness matters profoundly because bright galaxies require large populations of stars, and stars do far more than simply shine. Inside their cores, stars forge heavier elements like carbon, oxygen, and nitrogen, elements that didn't exist in any meaningful quantities immediately after the Big Bang. These elements are released only when stars die, scattering their enriched material into space. When Webb detects heavy elements in such young galaxies, it's observing evidence that earlier generations of stars must have already formed, lived their entire lives, and ended in spectacular death, all within the universe's first few 100 million years. The cosmic clock was being pushed backward. The universe didn't slowly ease into complexity. It accelerated toward it with surprising speed. Let your mind drift with these cosmic revelations. Feel yourself floating among distant galaxies. There's something quietly humbling about the act of observing this ancient light. Webb doesn't capture these images instantaneously. It gathers photons that have been traveling for more than 13 billion years. Photons that began their journey when the universe was young and unfamiliar, when everything looked profoundly different from today. When that light started moving through space, Earth didn't exist. Our sun hadn't formed yet. The Milky Way was still assembling itself from clouds of gas and mysterious dark matter, oceans, life, civilizations. Every single chapter of human history unfolded while those photons were already on their way toward us, crossing the incomprehensible distances between galaxies. By the time Webb detects them, we're not witnessing events happening now in real time. We're witnessing moments that occurred once, long ago, preserved in transit, and never to be repeated in quite the same way. This is why astronomers say James Webb doesn't just look far away into space. It looks backward through time itself. Distance becomes a timeline flowing from present to past. Nearby objects show us the universe closer to the present moment. Distant objects reveal earlier and earlier stages of cosmic history, reaching back toward the very beginning. Your body is completely relaxed now, your mind gently wandering through cosmic time. Yet, even Webb's extraordinary vision has a fundamental limit imposed by physics itself. No telescope, regardless of how powerful we might make it, can see beyond a boundary set by the nature of space-time. That boundary is defined by how far light has been able to travel since the universe began its expansion. It's called the observable universe, a vast sphere centered on us with a radius of approximately 46.5 billion light-years. Webb is now pushing observations closer to that boundary than ever before in human history, detecting galaxies at distances once thought forever unreachable. But even Webb cannot see beyond the cosmic horizon, and this is where the realization becomes deeply unsettling. Space doesn't stop at the edge of what we can observe. Beyond that horizon, galaxies still exist in uncountable numbers. Stars still ignite and die in their natural cycles. Black holes still merge in violent collisions. Entire cosmic histories unfold in regions forever hidden from our view. Not because our technology is lacking or because we haven't built powerful enough telescopes, but because the structure of space-time itself prevents observation. Space itself is expanding too rapidly, carrying distant regions away from us faster than light can travel to bridge the gap. James Webb has not only shown us how far our vision can reach into the cosmos, it has shown us how much of the universe lies permanently beyond our ability to observe, no matter how long we wait or how advanced our technology becomes. And as we absorb what Webb has revealed within our observable bubble, the early brightness, the rapid formation of structure, the sheer abundance of galaxies in every direction we look, a deeper question begins to emerge from the darkness. If this much exists in the small fraction of the universe we can see, what does that tell us about the true scale of everything that exists beyond our view? What wonders and mysteries populate the regions we can never reach? Let these questions drift through your consciousness as you sink deeper into rest. For most of modern astronomy's history, the early universe was imagined as a quiet and fragile place, still finding its footing. After the Big Bang released all energy and matter into existence, space expanded rapidly, temperatures dropped precipitously, and matter spread out almost evenly in every direction. Tiny fluctuations existed, regions that were slightly denser than others, but gravity was expected to work slowly and patiently, pulling matter together over vast spans of time. In this picture, the first stars ignited reluctantly, struggling against the conditions of the early universe. Gas needed time to cool sufficiently. Dark matter halos needed time to grow large enough. Galaxies, when they finally appeared, were expected to be small and faint, delicate structures that would take hundreds of millions of years to mature into anything substantial. The universe, according to this model, learned to walk before it learned to run. That expectation shaped decades of theoretical work and computer simulations. So when the James Webb Space Telescope began its detailed surveys of the early universe, astronomers anticipated scarcity, a few primitive galaxies scattered here and there, dim objects barely clinging to existence in a young cosmos still finding its way. Instead, Webb found crowds of galaxies wherever it looked, thriving communities of stars. Again and again, bright galaxies appeared in eras that should have been nearly empty according to our models. These weren't faint sparks barely holding together against the odds. They were already busy systems producing stars at rates comparable to, or even exceeding, those of much later cosmic epochs. The surprise wasn't the discovery of one strange, unexpected object that violated our theories. It was the pattern that emerged, the consistent finding that the early universe was far more active than anyone had predicted. Within the universe's first 500 million years, Webb detected galaxies emitting enormous amounts of light and energy. Some contained hundreds of millions, even billions of solar masses worth of material packed into relatively compact regions. That amount of mass should have required far more time to assemble than the universe had available at that early stage. Gravity is powerful, but it isn't instantaneously fast. Gas must lose energy through radiation before it can collapse into dense structures. Dark matter halos must accumulate enough mass to trap ordinary matter gravitationally. Stars take millions of years to form through the slow process of gravitational collapse. And those stars must live and die to enrich their surroundings with heavier elements. Each step imposes a minimum time scale. Compress the sequence too much, and the physics simply stops working according to our understanding. And yet, the galaxies were already there, fully formed and vigorously producing new stars. Feel yourself drifting deeper into relaxation. your consciousness expanding like the universe itself. One of the most unsettling aspects of these discoveries wasn't just the size or brightness of early galaxies, but their chemical maturity revealed through spectroscopic analysis. Webb's sophisticated instruments detected signatures of carbon, oxygen, and nitrogen in these ancient systems. Elements that don't exist in meaningful quantities immediately after the Big Bang. These elements are forged exclusively inside stars through nuclear fusion. Their presence in such young galaxies means something unavoidable and profound. At least one earlier generation of stars must have already formed, burned through their nuclear fuel, and ended their lives in supernova, spreading heavy elements into the surrounding space. All of this happened within the universe's first few 100 million years. The cosmic clock was being pushed backward even further than initial Webb observations suggested. To understand why this troubled astronomers so deeply, it helps to think of galaxy formation, like constructing a city from nothing. You cannot build skyscrapers before roads exist to transport materials. You cannot pour concrete before steel has been produced in factories. You cannot manufacture steel before iron ore has been mined and refined. Each stage depends fundamentally on the one before it, creating a minimum timeline for development. The early universe was supposed to be laying foundations, preparing the groundwork for later complexity. Webb found finished buildings already standing, complete architectural structures, when there should have been only construction sites. This growing mismatch between theoretical predictions and actual observations became known among astronomers as the too much light, too early problem. When researchers calculated how much total light galaxies should produce during the universe's first billion years based on our understanding of physics, their predictions fell significantly short. Webb's observations exceeded those predictions by factors of 2, 5, and sometimes even 10 times. That kind of discrepancy isn't a minor rounding error or measurement uncertainty. It's a signal that something fundamental in our understanding needs revision. Your breathing is so slow and peaceful now, like waves gently lapping at a cosmic shore. Scientists did what they always do when faced with something this profoundly unsettling. They questioned their measurements carefully. They rechecked the instruments for any potential errors. They reanalyzed the data using different methods. They asked whether dust obscuration, gravitational lensing effects, or observational biases could be making galaxies appear brighter or more massive than they truly were. Again and again, the result held firm under scrutiny. The early universe wasn't dim and sparse. It was luminous and crowded. Some of these early galaxies were so massive that researchers briefly referred to them as universe breakers, objects whose very existence seemed to violate the limits imposed by cosmology itself. According to standard models refined over decades, galaxies of that size simply should not exist at those early ages. Not unless something fundamental about early cosmic evolution was misunderstood or missing from our theories. At first, some astronomers hoped the masses were overestimated due to observational effects. Perhaps the light wasn't coming solely from stars. Perhaps supermassive black holes at galactic centers were contributing additional brightness through accretion processes, making galaxies appear larger and more massive than they really were. Further detailed analysis showed that this explanation helped resolve the discrepancy partially, but only partially. Yes, some early galaxies do host extremely active black holes, whose energy output inflates their apparent brightness significantly. Accounting for that contribution reduced the most extreme discrepancies with theoretical predictions. But even after those careful corrections were applied, the early universe still contained roughly twice as many massive galaxies as theory predicted. The tension eased somewhat, but it didn't disappear entirely. This pattern repeated across multiple independent surveys, conducted by different research teams. Webb looked in different directions at different regions of sky, using different instruments and wavelengths. Each time the fundamental result remained the same. The early universe was crowded with galaxies. Galaxy formation proceeded quickly and efficiently. Star formation operated with startling effectiveness compared to what our models predicted. Let these cosmic mysteries wash over you. Feel yourself becoming part of this ancient story. This forced astronomers to reconsider a basic assumption underlying their models. How, efficiently, could the early universe convert gas into stars? In the modern universe around us today, star formation is surprisingly inefficient at converting available material. Most of the gas inside galaxies never becomes stars at all. It gets heated by stellar radiation, stirred by turbulence, blown away by powerful stellar winds, or disrupted by energetic radiation from young massive stars. A massive molecular cloud may spend millions of years producing only a modest number of stars before dispersing back into space. Early galaxies appear to have played by different rules entirely, operating under conditions that favored much more rapid and efficient star formation. One possibility is that the early universe was simply denser overall, with matter packed more tightly together in a smaller volume of space. Gas clouds collided more frequently, triggering rapid gravitational collapse and star formation. Another idea is that the first stars formed from nearly pure hydrogen and helium, without heavier elements to complicate the cooling processes that allow gas to collapse. Under the right conditions, this simpler primordial gas may have collapsed more directly and efficiently than modern metal-rich gas does today. Galaxy mergers likely played a significant role as well. In the early universe, galaxies were much closer together on average. Collisions and mergers were far more frequent than in today's more spread-out cosmos. When galaxies merge together, their gas reservoirs are driven toward their centers, compressed to extreme densities that ignite intense bursts of star formation. A galaxy could build much of its stellar mass in short, violent merger episodes, rather than through slow, steady growth over billions of years. Each of these ideas helps explain part of the observed picture, yet none fully resolves all the discrepancies and questions that remain. Your mind is floating freely now, untethered from daily concerns, drifting through cosmic time. At the centers of many of these early galaxies lies another mystery entirely, one that compounds the puzzle. Webb has identified supermassive black holes already firmly in place when the universe was less than 500 million years old. Some of these black holes weigh millions, or even billions of times the mass of our Sun. According to conventional physics and our understanding of black hole growth, that simply should not be possible in such a short time. Black holes form when massive stars exhaust their nuclear fuel and collapse catastrophically. The resulting black hole may weigh tens of solar masses initially. From there, it can grow by consuming surrounding matter that falls past its event horizon. but that growth process has fundamental limits. As material falls inward, it heats up through friction and compression, radiating enormous amounts of energy that pushes back against further infall. This creates a natural speed limit on black hole growth, even under ideal conditions with abundant gas supply. Building a billion solar mass black hole should take far longer than the early universe allowed. Yet Webb keeps finding them, fully grown and actively feeding. This has forced astronomers to consider possibilities that once seemed extreme or speculative. Perhaps some black holes formed through the direct collapse of massive gas clouds in the early universe, skipping the stellar formation stage entirely. Perhaps the first generation of stars grew thousands of times more massive than modern stars can achieve, collapsing directly into surprisingly large black holes when they died. Perhaps black hole mergers were far more common in the dense early universe than we once assumed, allowing rapid mass growth through successive collisions. None of these ideas has been definitively confirmed yet, and none can be completely ruled out based on current evidence. What makes this early period so crucially important is that these nascent galaxies and black holes shaped absolutely everything that followed. Their radiation transformed the universe fundamentally, stripping electrons from hydrogen atoms throughout space during an era known as reionization. Their supernovae enriched space with heavy elements, seeding future generations of stars and planets. Their gravity pulled matter into the first large-scale structures that would eventually become the cosmic web we observe today. If they formed earlier and more efficiently than expected, then the entire timeline of cosmic evolution shifts, and we must revise our understanding of how structure emerged from the nearly uniform early universe. Let yourself sink even deeper, your consciousness expanding to embrace these cosmic scales. And as Webb continues to look deeper into space and time, the pattern becomes harder to ignore or explain away. The universe didn't wait patiently to become complex and structured. It rushed headlong toward complexity. It assembled stars, galaxies, and black holes at a pace that challenges our best equations and most refined models, which leads to an unavoidable realization. If the universe could build this much structure so quickly in its youth, then the scale of what exists today, after billions more years of continuous growth, may be far larger and more intricate than we ever imagined possible. And that realization becomes impossible to escape when Webb does something even more unsettling than finding early galaxies. It systematically counts how many galaxies actually exist throughout cosmic history. For most of the 20th century, astronomers believed they had reached a reasonable answer to one of the biggest questions imaginable. How many galaxies exist in the observable universe? The method was elegant in principle, even if extraordinarily challenging in practice. Point a powerful telescope at a tiny, seemingly empty patch of sky, far from the bright plane of the Milky Way. Count every single galaxy you can detect in that small region, and then scale that number up to cover the entire observable universe. When the Hubble Space Telescope performed its deepest observations in what became known as the Hubble Ultra Deep Field, it revealed nearly 10,000 galaxies in a region of sky no larger than a grain of sand held at arm's length. That image was profoundly shocking at the time, revealing a universe far more crowded than most people had imagined. From it, astronomers estimated that the observable universe contained a few 100 billion galaxies total, possibly as many as 200 billion. The number was almost impossible for the human mind to truly comprehend, and for years it stood as our best estimate. Then the James Webb Space Telescope looked at the same darkness with its infrared vision, and everything changed once again. Feel yourself floating among these countless galaxies, each one an island universe unto itself. Where Hubble saw black gaps between galaxies, Webb saw faint infrared glows revealing previously hidden structure. Where Hubble detected smudges barely rising above the background noise, Webb resolved detailed galactic structures. Regions that once felt empty suddenly revealed themselves as crowded, layered, and alive with distant systems that had been completely invisible to previous generations of telescopes. This difference wasn't a failure of Hubble's design or capabilities. It was simply a limitation of wavelength coverage. As the universe expands relentlessly, the light from distant galaxies stretches progressively into the infrared portion of the spectrum. By the time that ancient light reaches us across billions of light years, it no longer exists in the visible wavelength range that Hubble was primarily designed to study. The galaxies were always there, populating space. Their light had simply slipped past our eyes into wavelengths we couldn't detect. Webb was specifically built to catch it and bring those hidden galaxies into view. In one of its most ambitious observational programs, Webb surveyed a region of sky only slightly larger than 3 full moons placed side by side, a tiny fraction of the total sky. For hundreds of hours, it patiently collected more than 10,000 individual exposures, each one capturing faint infrared signals that had traveled across cosmic time. When those thousands of images were carefully combined and processed, the result was absolutely staggering to astronomers. Nearly 800,000 distinct galaxies filled the frame. 800,000 separate island universes in a patch of sky most people would dismiss as empty darkness. To grasp the true scale of that result, imagine printing the famous Hubble Ultra Deep Field image on a standard sheet of paper. To show the Webb Deep Field image at the same level of detail and resolution, the print would need to be more than 13 feet tall and 13 feet wide. A wall-sized mural of cosmic history, and every single point of light in that vast mural isn't a star within our galaxy. It's an entire galaxy in its own right. Let that sink in as you drift deeper into rest. 800,000 galaxies in one small patch of sky. Each of those galaxies contains millions, billions, or even trillions of individual stars. Many host planetary systems orbiting those stars. Many contain complex chemistry, playing out in nebulae and stellar atmospheres. Dust lanes and heavy elements forged by generations of stars living and dying. The universe, it turns out, is not sparsely populated with isolated islands of matter drifting through vast emptiness. It is densely packed and layered with structure at every scale we examine. What makes this discovery even more powerful scientifically is that Webb didn't simply count galaxies like tallying points of light. It measured them systematically. For each galaxy, astronomers can estimate its distance based on redshift, its total mass from brightness and structure, its rate of star formation from spectroscopic signatures, and its approximate age. That allows scientists to reconstruct how galaxies changed over nearly the entire history of the universe. tracking growth and evolution from early cosmic dawn to the present day. And when they compiled that data and analyzed those patterns, a deeper structure emerged from the numbers. Galaxies are not scattered randomly through space, like salt spilled on a table. They cluster together. They align into patterns. They trace invisible pathways through the cosmos. On the largest scales, the universe resembles a vast cosmic web, long filaments of matter, stretching tens and hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, and separated by enormous voids where almost nothing exists at all. Your consciousness expands to perceive this cosmic web. Feel its elegant structure. This large-scale structure had been predicted for decades based on theoretical models and computer simulations. But Webb revealed it with unprecedented clarity and detail. Many of the galaxies Webb detected were hidden behind thick dust that completely blocks visible light, but graciously allows infrared wavelengths to pass through relatively unimpeded. Entire populations of dusty, star-forming galaxies suddenly appeared in the census, filling in gaps where earlier surveys saw apparent emptiness. The cosmic web didn't just become clearer through Webb's observations. It became noticeably more crowded with structure. This matters profoundly because the distribution of galaxies throughout space is not random decoration without meaning. It is a permanent record of how the universe grew from initial conditions. Shortly after the Big Bang, matter was spread almost perfectly evenly throughout space, with only tiny fluctuations in density imprinted during the universe's earliest moments of existence. Regions that were slightly denser than average by even tiny fractions exerted slightly stronger gravitational pull on their surroundings. Over vast spans of time, matter flowed gradually toward those denser regions, amplifying the initial differences. Gravity slowly but inexorably carved space into an intricate network of filaments and nodes, draining matter from surrounding regions and leaving behind vast cosmic voids. A useful analogy is rainfall over terrain with varied elevation. Water naturally drains into valleys and low points, carving rivers and channels as it flows, while higher ground is gradually left dry. Over time, a complexly structured landscape emerges from initially smooth topography. The universe evolved in much the same way, except the flowing substance was matter itself, and the driving force was gravity, acting over billions of years. Let these cosmic currents carry you deeper into peaceful sleep. Webb's observations demonstrate that this structure-forming process was already remarkably well underway, surprisingly early in cosmic history. Filaments tens of millions of light years in length existed when the universe was only a few billion years old. Some structures were so large and so organized that they challenged expectations about how quickly matter could arrange itself gravitationally. One particularly striking example is a structure astronomers have nicknamed the cosmic vine. It's a chain of at least 20 closely packed galaxies, stretching more than 13 million light-years across the cosmos. These galaxies existed when the universe was still quite young by cosmic standards. Yet the structure rivals much older formations in both size and organization. What makes the cosmic vine especially intriguing isn't just its impressive scale, but its evolutionary state. Several of its largest member galaxies have already stopped forming new stars entirely. They are quiescent, meaning they have exhausted or somehow lost the gas reservoirs needed to create new stars. This is unusual and unexpected so early in cosmic history, during an era when most galaxies throughout the universe are still actively forming stars at substantial rates. The implication is profound. Environment matters tremendously for galaxy evolution. Galaxies in dense regions evolve differently than isolated ones drifting through cosmic voids. Gravitational interactions, mergers, and the harsh environmental conditions of crowded space can dramatically accelerate a galaxy's life cycle, forcing it to grow rapidly, consume its gas quickly, and burn out early compared to galaxies in quieter environments. And this is not an isolated case or unusual exception. Using Webb's data, astronomers have compiled the deepest and most comprehensive catalog of galaxy groups ever assembled. They identified more than 1,600 distinct galaxy groups and protoclusters, spanning cosmic time from about 12 billion years ago to just a few billion years ago. These groups represent the building blocks of today's massive galaxy clusters, the seeds from which the largest structures in the universe grew. By comparing groups at different distances, and therefore different cosmic ages, scientists can watch structure formation unfold over billions of years, like a cosmic time-lapse. Early groups appear chaotic and disorganized, with irregular galaxies forming stars at prodigious rates. Later groups show more order and organization. Galaxies become smoother and more regular in appearance. Star formation gradually slows, and gravity begins to dominate over turbulence and fresh gas inflow. This continuous view across billions of years of cosmic history was simply not possible before Webb's infrared capabilities opened our eyes. Your mind drifts peacefully through this cosmic web, following ancient pathways. Yet for all this density and intricate organization, the universe is also profoundly defined by its vast emptiness. Between the bright filaments of the cosmic web lie enormous voids, regions spanning tens to hundreds of millions of light-years that contain very few galaxies at all. These cosmic voids are not small gaps or minor features. They are actually the largest contiguous structures in the universe, by total volume. If you could somehow place yourself at the center of one of these voids and look outward in any direction, you would see darkness stretching for tens of millions of light-years before encountering the nearest significant galaxy. Entire regions of space failed to accumulate matter simply because gravity pulled that matter elsewhere along cosmic filaments. Webb's deep field images capture this striking contrast vividly. In the same observational frame, dense clusters of galaxies appear alongside yawning black regions containing almost nothing. The universe is simultaneously crowded and empty, rich and sparse, intricately structured and desolately barren, depending on precisely where you direct your gaze. This brings us back to those staggering numbers revealed by Webb's surveys. If Webb's deep fields are representative of the universe as a whole, and multiple observations in different directions strongly suggest they are, then the total number of galaxies in the observable universe may not be hundreds of billions as previously estimated. It may be trillions, perhaps 2 trillion galaxies, or even more. For every galaxy we once thought existed, there may be 10 more hiding in the infrared, beyond what earlier telescopes could detect. That revision changes everything about our perception of cosmic scale. More galaxies mean exponentially more stars. More stars mean vastly more planetary systems. More planets mean dramatically more opportunities for complexity, chemistry, and perhaps even life to arise and flourish. The universe becomes not just physically larger in extent, but immeasurably richer in possibility and potential. Feel the vastness surrounding you. Embrace the infinite possibilities. Yet even this staggering abundance of trillions of galaxies exists only within the observable universe, the bubble of space from which light has had time to reach us. Beyond that observational boundary, space continues without end. Galaxies continue forming and evolving. Structure continues developing under gravity's patient influence. James Webb has shown us that even the portion of the universe we can observe is vastly larger and more densely populated than we believed just a few years ago. And that profound realization forces an even deeper question to emerge from the cosmic darkness. If reality is this rich and complex within our visible horizon, what does that tell us about the true scale of everything we can never observe? What lies beyond the cosmic edge of observability? How much more exists in regions forever hidden from our view? At first glance, the universe seems straightforward to measure and comprehend. The Big Bang occurred approximately 13.8 billion years ago. Light travels at a fixed, constant speed through space, so it feels intuitively natural to assume that the farthest objects we can see should be located about 13.8 billion light-years away from us. For a long time, even professional scientists spoke about the universe as if that simple picture were accurate. But that intuition quietly breaks down the moment we take cosmic expansion seriously and think through its implications carefully. The observable universe does not have a radius of 13.8 billion light-years, as intuition might suggest. It has a radius of approximately 46.5 billion light-years, making its full diameter roughly 93 billion light-years across. This is not speculation or theoretical extrapolation. It is a measured result, firmly supported by observations of cosmic expansion rates and the behavior of ancient light traveling across the universe. Let your mind expand to encompass these impossible distances. The reason this number feels impossible and contradictory is because it clashes fundamentally with how we instinctively think about motion and distance. Nothing can travel faster than light through space itself. That cosmic speed limit is absolute, and that rule still holds true without exception. No galaxy is racing through space at impossible velocities. No signal is somehow breaking the cosmic speed limit. Instead, the universe has found a way to grow far larger than expected, without violating any known laws of physics. It accomplishes this remarkable feat by stretching space itself, expanding the very fabric of space-time between distant objects. When we say distant galaxies are moving away from us, it's tempting to picture them flying outward through space, like fragments from an explosion, racing away from a central point. That mental image is deeply misleading and fundamentally incorrect. On cosmological scales, galaxies aren't really moving through space at all in the conventional sense. They're being carried apart passively as the space between them expands, like an inflating balloon. A familiar analogy helps make this counterintuitive concept more intuitive. Imagine dots carefully drawn on the surface of a balloon. As the balloon inflates steadily, every dot moves farther away from every other dot automatically. None of the dots are located at any special center point. None of them are moving across the rubber surface under their own power. The surface itself is stretching uniformly, and the dots simply go along for the ride, carried by the expanding substrate. The universe behaves in precisely the same way on its largest scales. Your breathing is so slow and deep now, perfectly relaxed and peaceful. When a distant galaxy emitted the ancient light we detect today with our telescopes, it was actually far closer to us in space than it is at this present moment. Over billions of years, while that light was steadily traveling toward Earth at light speed, the space between us and that distant galaxy expanded continuously and relentlessly. By the time the light finally arrived at our telescopes after its long journey, the galaxy that originally emitted it had been carried tens of billions of light years farther away by cosmic expansion. This is why we can observe galaxies whose light has been traveling for 13.5 billion years, even though their current distance from us is more than 46 billion light years away. Light isn't simply crossing a fixed distance through static space. It's moving through a distance that is actively growing while the light travels. In effect, light has been running on a cosmic treadmill that keeps stretching longer. Early in the universe's history, expansion was slower and more gradual. Light made steady progress toward us. As cosmic time passed, expansion gradually accelerated, stretching distances faster and faster under the influence of dark energy. Some photons managed to reach us because they started their journey early enough, before the expansion rate became overwhelming. Others never will reach us, no matter how long we wait. This creates what astronomers call the cosmic horizon, an observational boundary beyond which we cannot see. The cosmic horizon is not a physical wall or an edge where space suddenly stops existing. There is no location where the universe abruptly ends, like the edge of a table. Instead, it represents the ultimate limit of what can ever be observed from our specific location in space and time. Given the finite age of the universe and the way space expands at accelerating rates, beyond that horizon, light simply cannot reach us. Not because it lacks sufficient time, but because the space it must cross grows faster than light can traverse it. And this is where contemplating the universe becomes deeply unsettling on a philosophical level. Feel yourself floating at the edge of observability, gazing into the unknowable beyond. Space does not end at the cosmic horizon. We know this with considerable confidence because the universe looks essentially the same in every direction we observe. The distribution of galaxies doesn't thin out toward any edge. The cosmic microwave background radiation, that faint afterglow of the Big Bang itself, appears almost perfectly uniform across the entire celestial sphere. That remarkable smoothness and uniformity would be absolutely impossible if space abruptly ended just beyond our observable view. So the universe unquestionably extends beyond what we can see, but it does so in a way that permanently hides vast regions from our observation. Beyond 46.5 billion light years, galaxies still exist in unimaginable numbers. Stars still ignite in nebulae and die in supernovae. Black holes still merge in cataclysmic collisions releasing gravitational waves. Entire cosmic histories unfold across billions of years, in regions that will never influence us, and can never be influenced by us. No signal from those distant regions will ever reach Earth, no matter how long humanity or its descendants might wait. Not because our technology is inadequate, or our telescopes insufficiently powerful, but because the fundamental structure of space-time itself prevents that information from ever arriving. Even more profoundly unsettling, this observational boundary is not fixed in place permanently. As cosmic time passes, the observable universe grows gradually larger, because light from more distant regions has had more time to reach us across expanding space. The horizon creeps slowly outward, but simultaneously, cosmic expansion is accelerating continuously, driven by the mysterious dark energy that permeates all of space. Space itself is stretching faster now than it did in the past, and that rate continues increasing. These two effects compete with one another in a cosmic race. The result is a universe where some objects briefly become observable for a limited time, only to later slip beyond reach forever, as expansion carries them away. Galaxies we can see today are not guaranteed to remain visible indefinitely into the future. Their light will continue to stretch as space expands, shifting into longer and longer wavelengths, becoming progressively more red-shifted. Eventually, that light becomes so diluted and stretched that no conceivable telescope could ever detect it against the background glow. From our perspective, those galaxies will appear frozen at a particular moment in their evolutionary history, slowly fading like ghosts until they vanish completely from view. Let yourself drift with these cosmic currents, feeling smaller and larger simultaneously. This is not merely a theoretical curiosity or abstract thought experiment. It is a direct consequence of measured expansion rates and well-established physics. If the universe continues behaving as it does now, with accelerating expansion, then in roughly 100 to 150 billion years, every galaxy outside our local gravitationally bound group will cross beyond the cosmic horizon. Future observers living in that distant era would see a universe containing only a small cluster of nearby galaxies, surrounded by vast cosmic darkness. The evidence of cosmic expansion, the cosmic microwave background radiation, and the vast web of distant galaxies would all be gone, erased from view, not by time, but by space itself. Those future observers might never know that anything else ever existed beyond their local neighborhood. They would be cosmologically isolated in a way we are not yet. This leads to a profound shift in perspective that changes how we think about reality itself. The observable universe is not the universe in totality. It is simply the portion of the universe that happens to be observable from where we stand at this particular moment in cosmic time. Move to another galaxy far away, and the observable universe changes significantly. Different galaxies enter view, while others disappear beyond the horizon of that new vantage point. Every location in space defines its own observable universe, its own bubble of causally connected space-time. This creates strange and deeply counterintuitive situations that challenge our assumptions. Two galaxies can both be observable from Earth, yet completely unable to observe each other across space. They may lie on opposite sides of our cosmic horizon. Light from both reaches us, traveling in different directions, but light from one cannot reach the other before expansion carries them too far apart. From their perspectives, Earth itself may lie beyond their cosmic horizon, forever unobservable. There is no privileged vantage point anywhere in the universe, no center from which everything can be seen, no location from which the entire cosmos is laid out for observation. Every observer, no matter where they exist in space, sits at the apparent center of their own observable bubble, surrounded by their own unique cosmic horizon. This is the profound principle of cosmic mediocrity, carried to its ultimate conclusion. Your mind floats freely through infinite space, unbound by horizons. This is precisely why the James Webb Space Telescope is so profoundly transformative for our understanding. By pushing observations closer to the cosmic horizon than ever before in human history, Webb forces us to directly confront the ultimate limits of what observation can achieve. When Webb detects galaxies at extreme redshifts near the edge of observability, it is not just showing us ancient objects from cosmic dawn. It is showing us the very boundary of causal connection in our universe. Those galaxies are no longer located where their light began its journey toward us. They have been carried much farther away by billions of years of expansion. Their current state, their later mergers and transformations, their evolved stellar populations, and their possible eventual destruction, all of that is fundamentally unknowable to us. That information is still traveling through space somewhere, stretched and diluted by ongoing expansion. And in many cases, that information will never arrive at Earth. The galaxies will recede beyond our cosmic horizon before their light can complete its journey. What we see is not what currently is. It is what once was, preserved in ancient photons. And even that historical view is incomplete and fragmentary. Beyond the observable horizon lies the unobservable universe, regions that may contain galaxies, clusters, and cosmic structures just as rich and complex as those we can see within our bubble. Some cosmological models suggest the universe may be truly infinite in extent, stretching forever without end. Other models propose it is finite, but unimaginably vast, wrapping back on itself in ways difficult to visualize. Either way, the observable universe is almost certainly only a small fraction of the whole, perhaps a tiny fraction. James Webb has not revealed any edge to the universe itself. It has revealed that there is no accessible edge at all, from our perspective, only an ever-present horizon defined by light and time. Feel yourself at peace with this cosmic mystery, accepting what cannot be known. And as this profound realization settles gently into consciousness, another question becomes unavoidable and pressing. If most of the universe is permanently hidden by expansion, if vast regions of reality are forever beyond our observational reach, then something powerful must be driving that expansion to accelerate continuously. To understand that mysterious force, we must confront the most dominant and yet most mysterious ingredient of the cosmos itself: dark energy. For most of the 20th century, the story of cosmic expansion seemed relatively straightforward despite its grandeur. The universe began in the Big Bang, roughly 14 billion years ago. Everything rushed outward in all directions, and gravity gradually worked to slow that initial expansion down over time. Astronomers vigorously debated whether the universe would expand forever, gradually slowing but never quite stopping, or eventually collapse back in on itself in a reverse of the Big Bang. But the underlying assumption was fundamentally the same in every theoretical scenario. Gravity was in control of the universe's fate. That seemingly solid assumption did not survive contact with actual observation in the late 1990s. In that pivotal decade, astronomers studying distant stellar explosions across the cosmos noticed something deeply unsettling and completely unexpected. These explosions, known as type Ia supernovae, shine with a remarkably consistent peak. brightness because of their underlying physics. Because of that predictable reliability, they act like cosmic mile markers, standardized candles allowing distance measurements. By comparing how bright a supernova appears from Earth to how bright it should be intrinsically, scientists can calculate its distance with good accuracy. Combine that distance measurement with how fast the host galaxy is receding from us, measured through redshift, and the expansion history of the universe reveals itself through careful analysis. What those painstaking measurements showed was the exact opposite of what anyone expected or predicted. The universe was not slowing down its expansion under gravity's influence. It was speeding up instead, accelerating. Your heartbeat slows to match the rhythm of cosmic expansion. Distant galaxies were significantly farther away than they should have been if expansion were gradually easing under gravity's restraining pull over billions of years. Something was actively pushing space apart, not just preserving the initial expansion momentum, but actively accelerating it over time. The farther back in time astronomers looked using increasingly distant supernovae, the clearer the troubling pattern became. Expansion had been gaining speed for billions of years, accelerating throughout recent cosmic history. To account for this completely unexpected behavior, cosmology was forced to introduce an entirely new ingredient into its equations, something that came to be called dark energy. Dark energy is not something we can see directly, touch physically, or detect through any conventional means. It does not emit light or any other form of electromagnetic radiation. It does not absorb light passing through it. It does not clump into structures like stars, galaxies, or diffuse clouds. Its existence is inferred entirely and completely from its effect on the universe's expansion rate, observed through multiple independent methods, and that effect is utterly overwhelming in its magnitude. Current measurements now indicate that dark energy constitutes roughly 68% of everything that exists in the universe, more than 2/3 of all reality. Ordinary matter, everything from galaxies and stars to planets, atmospheres, and living organisms, accounts for less than 5% of the total. Dark matter, that other mysterious invisible component, makes up most of the remainder. The universe we can see and touch and measure directly, the universe that feels solid and familiar and real, is a relatively minor component of total reality. What makes dark energy especially unsettling and mysterious is how it behaves fundamentally differently as the universe grows larger. Normal matter becomes progressively diluted as space expands continuously. Double the volume of space, and the average density of matter drops by half. Simple as that. Radiation thins out even faster, its energy decreasing as wavelengths stretch. Dark energy does not follow these intuitive rules at all. Its density remains essentially constant, even as the universe expands dramatically. As space grows larger over billions of years, the total amount of dark energy increases proportionally. More space automatically means more dark energy filling that space. Let this cosmic strangeness wash through your consciousness. This creates a runaway feedback effect that compounds over time. More space means more total dark energy. More dark energy drives faster expansion. Faster expansion creates yet more space in a self-reinforcing cycle. Over billions of years, this relentless feedback loop has fundamentally shifted the balance of power in the universe. Early in cosmic history, ordinary and dark matter dominated gravitationally. Gravity sculpted the first galaxies, stars, and the intricate cosmic web we observe. But as the universe expanded and matter spread progressively thinner, dark energy quietly accumulated and took over cosmic dynamics. About 5 billion years ago, a pivotal transition occurred. Dark energy became the dominant influence on cosmic expansion, exceeding matter's gravitational restraint. The James Webb Space Telescope does not detect dark energy directly through any instrument or sensor, but it sees its distinctive fingerprints everywhere it looks. The extreme stretching of ancient light across billions of years. The immense size of the observable universe, extending 93 billion light-years, and the way distant galaxies recede at accelerating rates, all reflect the pervasive influence of this invisible force filling all of space. Without dark energy driving accelerated expansion, the universe would be far smaller and younger looking. The cosmic horizon would sit much closer to us. Vast regions we can observe today would never have been observable at all, because their light couldn't have reached us. Dark energy does far more than merely shape the present cosmic conditions we observe. It determines the universe's ultimate future fate over trillions of years. If dark energy remains constant in strength, as current observations strongly suggest, then expansion will continue forever without end, steadily accelerating as cosmic time passes into the incomprehensible future. Galaxy clusters that are currently gravitationally bound will remain so, held together by their mutual gravity. But everything outside those bound systems will gradually slip beyond the cosmic horizon one by one. Trillions upon trillions of years from now, observers inside a galaxy like our Milky Way would inhabit a profoundly lonely cosmos, filled with familiar stars nearby in their local group, but appearing utterly empty beyond that small region. An island of light in an ocean of expanding darkness. The universe would still exist in its full grandeur, but it would appear almost vacant from any one vantage point. A cosmic isolation ward. Feel yourself drifting peacefully toward that distant future, embracing the eternal silence. Yet this picture of the far future is complicated significantly by one of the most serious unresolved problems in modern cosmology. A problem that James Webb has not erased or explained, but has instead made considerably harder to ignore through its precise measurements. When scientists measure how fast the universe is expanding today, using different observational methods, they do not get one consistent answer as expected. They get two distinctly different values that refuse to reconcile. One method looks deep into the cosmic past by carefully studying the cosmic microwave background radiation, that faint afterglow released when the universe was only about 380,000 years old, and matter first became transparent to light. From the subtle patterns and fluctuations in that ancient radiation, scientists can infer an expansion rate of approximately 67 kilometers per second per megaparsec, meaning galaxies separated by 1 megaparsec of space recede from each other at 67 kilometers per second. The second method looks relatively nearby in cosmic terms. Astronomers measure distances to galaxies using Cepheid variable stars and type Ia supernovae as calibrated standard candles, then compare those distances to how fast the galaxies are receding based on redshift measurements. This local approach consistently produces a measurably higher value, around 73 kilometers per second per megaparsec, significantly above the other measurement. Both measurements are remarkably precise, with small error bars. Both have been repeated many times by independent research teams. Both have been exhaustively scrutinized for potential systematic errors and observational biases. They simply do not agree with each other, and the discrepancy exceeds the measurement uncertainties by a statistically significant margin. This troubling discrepancy is known among cosmologists as the Hubble tension, and it represents one of the deepest cracks currently visible in our understanding of the universe's fundamental behavior. James Webb was widely expected to help clarify this confusing situation by providing cleaner, more accurate distance measurements, using improved observational capabilities and infrared sensitivity. Instead, Webb's initial results have confirmed and strengthened the higher expansion rate measured in the nearby universe using local methods. The tension did not disappear or reduce as hoped. If anything, it sharpened and became more statistically robust. Your mind accepts this cosmic puzzle without anxiety, floating peacefully through uncertainty. This leaves cosmology in a decidedly uncomfortable position that demands resolution. Either something is subtly wrong with our measurement methods in ways we haven't identified, something is wrong with our foundational assumptions about how the universe behaves, or something fundamental is genuinely missing from our theoretical models of reality. One intriguing possibility is that dark energy is not actually constant in strength across all of cosmic history, after all. Its effective strength may have changed over billions of years, subtly altering the expansion rate in ways our current models don't properly capture or account for. Another possibility is that unknown physics affects how light travels across enormous cosmic distances, subtly biasing our measurements in ways that create apparent discrepancies. Or perhaps the early universe itself behaved differently than we assume in our models, imprinting expansion behavior that evolves in unexpected ways we haven't considered. Each possibility carries profound consequences for our understanding. The expansion rate fundamentally determines the universe's age, its current size, and its ultimate fate over incomprehensible stretches of time. If we are misunderstanding something this fundamental, then many conclusions drawn from decades of careful cosmological research may need significant revision. Entire theoretical frameworks might require rethinking. The problem is not merely cosmetic or a minor detail to be cleaned up. It cuts directly to the foundation of how we describe reality mathematically. There is also a more extreme scenario that cannot yet be definitively ruled out based on current observations. If dark energy somehow grows progressively stronger over time instead of remaining constant, expansion could eventually overwhelm gravity, even on progressively smaller scales. Galaxy clusters would be torn apart over trillions of years. Galaxies themselves would dissolve as space between their stars expands faster than gravity can hold them together. Star systems would be disrupted. Planets would be pulled from their orbits. Molecules could be torn apart. And eventually, even atoms themselves could be ripped apart in a hypothetical future apocalypse cosmologists call the Big Rip. Current observational data does not favor this dramatic outcome, but significant uncertainties remain in our understanding. Measuring dark energy's behavior precisely is extraordinarily difficult technically, and small changes in its properties could have enormous long-term consequences. Let these mysteries dissolve into peaceful acceptance. release the need to know everything. What is already abundantly clear from multiple lines of evidence is that dark energy dominates the cosmos on its largest scales. It stretches space relentlessly, hides vast regions of reality permanently beyond our observational reach, and determines what future observers will be able to see across cosmic time. It is the fundamental reason the observable universe spans 93 billion light-years, rather than a smaller sphere. It is the reason most of existence will forever remain invisible to us, hidden not by distance alone, but by the very nature of space-time. And yet, dark energy alone does not explain the richly structured universe we observe through our telescopes, because while it pulls space apart, inexorably, on the very largest scales, something else must simultaneously pull matter together on smaller ones. Something must locally counter expansion, allowing galaxies to form and persist, clusters to grow more massive, and cosmic structure to emerge and evolve, rather than simply dissolving into uniform fog spread across expanding space. That essential force is equally invisible to direct observation, equally mysterious in its fundamental nature, and absolutely essential to everything we see. To understand how the universe holds itself together, even as it expands, we must turn our attention to the unseen framework that shapes every galaxy, every cluster, and every filament of the cosmic web. Feel yourself cradled by invisible forces, held gently in gravity's embrace. If dark energy governs how the universe expands on cosmic scales, then dark matter governs how structure holds itself together against that expansion. Without dark matter's gravitational influence, the universe revealed by the James Webb Space Telescope would not exist in any recognizable form we could observe. Galaxies would never have assembled in the first place. Clusters would have flown apart before forming, and the vast filamentary structure, stretching across billions of light-years, would have remained merely a nearly uniform fog of matter, without organization. Dark matter does not shine with any wavelength of light. It does not absorb electromagnetic radiation. It does not emit any form of radiation we can directly detect with any instrument yet devised. And yet, it outweighs everything we can see by more than 5 to 1 in total mass. Roughly 85% of all matter in the universe is dark matter, detectable only through its gravitational influence on visible matter and light. Every star, planet, nebula, and galaxy is built within an invisible framework, dominated by something fundamentally invisible to our eyes and instruments. The visible universe floats within an unseen ocean. The first observational clues to dark matter's existence emerged nearly a century ago, when astronomers noticed that galaxies were behaving in ways that made absolutely no sense according to visible matter alone. Stars in the outer regions of spiral galaxies were orbiting far too rapidly around the galactic center. According to the gravity generated by visible stars and gas that astronomers could detect and measure, those outer stars should have been flung into intergalactic space long ago by centrifugal effects. Instead, they remained gravitationally bound, orbiting steadily, as if each galaxy were embedded in a massive unseen halo of invisible matter, providing additional gravitational pull. That unseen mass was dark matter, though it wouldn't be called that for many years. Your consciousness expands to perceive the invisible scaffolding of reality. As observations expanded to include entire galaxy clusters and large-scale structure, the evidence became progressively impossible to ignore or explain away. Entire galaxy clusters showed the same fundamental problem on much larger scales than individual galaxies. Individual galaxies within clusters move far too quickly relative to each other to be held together gravitationally by visible stars and gas alone. They should disperse into space, yet they remain bound. Gravitational lensing observations revealed distortions in background galaxies, far stronger than visible matter in foreground clusters could possibly produce. Invisible mass was bending light. Again and again, the unavoidable conclusion emerged from independent observations. Most of the universe's matter is completely invisible to electromagnetic observation. What makes dark matter so crucially important is not just the quantity that exists, but how it behaves fundamentally differently from ordinary matter. Unlike normal matter, dark matter does not collide meaningfully with itself or lose energy by emitting radiation through electromagnetic interactions. It passes through space almost frictionlessly, interacting only through gravity. This allowed it to begin clumping together extraordinarily early in cosmic history, long before ordinary matter could collapse. Shortly after the Big Bang, the universe was nearly uniform in density, with only tiny statistical fluctuations imprinted during its earliest moments of existence. Dark matter responded to those subtle fluctuations first and most dramatically, while ordinary matter remained hot and ionized, prevented from collapsing by radiation pressure. Dark matter quietly gathered into growing concentrations, forming massive invisible halos, long before the first stars ever ignited. These dark matter halos became the gravitational scaffolding of the entire universe, the framework upon which everything else would eventually build. As the universe gradually cooled over hundreds of millions of years, ordinary matter began falling into these pre-existing dark matter gravitational wells. Gas collected, compressed, and eventually reached temperatures and densities sufficient to ignite nuclear fusion. Stars formed, galaxies assembled, not randomly scattered through space, but precisely where dark matter had already patiently gathered over eons. The visible universe traces an invisible blueprint laid down billions of years earlier by dark matter's gravitational choreography. Let yourself sink deeper into rest, feeling the invisible foundations supporting all existence. This prolonged process produced one of the most visually striking features of cosmic reality: the cosmic web we observe stretching across the universe. On the largest scales spanning hundreds of millions of light years, matter is arranged in vast filaments of galaxies and dark matter stretching across the cosmos. These filaments intersect at extremely dense nodes, where massive galaxy clusters form under intense gravitational attraction. Between the bright filaments lie enormous cosmic voids, regions so remarkably empty they contain almost no galaxies at all, across tens of millions of light years. This large-scale structure is not artistic coincidence or random chance. It is the natural, inevitable outcome of gravity, acting on dark matter over billions of years of cosmic time, amplifying initial density fluctuations into pronounced structure. James Webb's unprecedented observations have brought this cosmic architecture into sharper focus than ever before in history. By cataloging hundreds of thousands of galaxies and measuring their individual distances through redshift, astronomers can construct detailed three-dimensional maps of matter distribution across vast volumes of space. The pattern is unmistakable, and stunning in its clarity. Galaxies line up along filaments like beads on cosmic strings. They cluster at intersection points. They avoid vast, empty regions. The visible universe faithfully follows an invisible skeleton of dark matter. What makes Webb especially powerful for mapping structure is its ability to see through obscuring dust and detect faint, distant galaxies that previous surveys completely missed. This fills in critical gaps in the cosmic web, revealing how remarkably early these large-scale structures emerged after the Big Bang. Webb has demonstrated conclusively that filaments were already well established when the universe was only a few billion years old. Matter was already flowing along them into growing clusters, building structure faster than many theoretical models predicted. This flow is not just a poetic metaphor. Both simulations and observations indicate that gas actually streams along dark matter filaments, like traffic flowing along cosmic highways, feeding growing galaxies with fresh material. Galaxies grow not only by forming stars internally from their own gas reservoirs, but by continuously accreting fresh material delivered along these invisible supply routes over billions of years. Even our own Milky Way galaxy participates actively in this cosmic process. We reside within a filament connecting to larger structures, drifting through space along pathways defined entirely by invisible dark matter distribution. Feel yourself floating along cosmic currents, following ancient paths through expanding space. On these vast scales, motion is guided and determined by structure, not random. Galaxies don't simply drift aimlessly, but follow gravitational flows carved out by dark matter over cosmic history. For decades, the fundamental role of dark matter in shaping the cosmic web rested largely on computer simulations and indirect evidence from visible matter distribution. But recently, astronomers achieved something quite remarkable using advanced observational techniques. They detected dark matter directly along the filaments themselves, measuring its gravitational effects. Using subtle gravitational lensing effects, scientists measured how light from distant background galaxies was slightly but measurably distorted as it passed through regions where filaments were predicted to exist, based on visible galaxy distribution. The distortions were extraordinarily faint and difficult to detect above observational noise, requiring years of careful analysis. But they were statistically significant and consistent with predictions. They revealed substantial mass present, where no visible matter could account for it whatsoever. Dark matter was not just concentrated in galaxy clusters, as previously known. It was stretched across intergalactic space, threading the entire universe together into an interconnected network. This observational confirmation transformed the cosmic web from a theoretical construct in computer simulations into a directly measured physical structure. The universe is not a loose collection of galaxies gradually drifting apart in expanding space. It is an intricately interconnected network, shaped and sustained by invisible matter we cannot see, but can detect gravitationally. The nodes of this vast network are galaxy clusters, the most massive gravitationally bound objects in the entire universe. A single rich cluster can contain hundreds or thousands of individual galaxies, along with vast reservoirs of superheated X-ray emitting gas and truly enormous quantities of dark matter binding everything together. These clusters act as gravitational anchors, pulling matter along filaments toward their centers over billions of years. When galaxies fall into clusters attracted by intense gravity, they experience dramatic and often violent changes to their structure and evolution. The dense cluster environment strips away gas through ram pressure and tidal forces, shutting down star formation relatively quickly, reshaping galactic structure through gravitational interactions, transforming spiral galaxies into passive ellipticals over time. James Webb has captured these dramatic transformations in remarkable detail, showing galaxies caught mid-transition as they are profoundly altered by their crowded surroundings. The cosmic web is not static or frozen. It is dynamic, active, and constantly reshaping the universe we observe. Structure continues evolving even today. Your mind drifts peacefully through this invisible architecture, at peace with mystery. Yet for all its overwhelming influence throughout the cosmos, dark matter remains one of the greatest unsolved mysteries in all of physics. We still do not know with any certainty what it is fundamentally made of at the particle level. It may consist of unknown exotic particles beyond the standard model of particle physics. It may involve entirely new physics we haven't discovered yet. It could be something we haven't even imagined. Despite decades of increasingly sophisticated experiments, both in particle accelerators and in deep underground detectors, dark matter has never been directly detected in a laboratory setting. We cannot capture it, examine it, or study its properties directly. And still, despite this profound ignorance, its presence throughout the universe is absolutely undeniable, based on gravitational evidence. Every galaxy rotation curve measurement, every gravitational lensing map, every large-scale structure survey points inexorably to the same fundamental conclusion. Remove dark matter from the cosmological equations, and the universe we actually observe simply cannot exist mathematically. The numbers don't work. The structure doesn't form. The galaxies fly apart. James Webb does not solve the dark matter mystery or reveal its fundamental nature, but it dramatically strengthens the observational case for its absolutely central role in cosmic evolution. By revealing how quickly structure formed in the early universe through its deep field observations, Webb shows convincingly that visible matter alone could never have accomplished the gravitational work required. Dark matter provided the essential gravitational head start needed to assemble galaxies just a few 100 million years after the Big Bang. Without that invisible scaffolding already in place, the universe would look completely different today. It also explains naturally why the universe exhibits the specific appearance it does on large scales. The vast emptiness of cosmic voids, the concentrated richness of galaxy clusters, and the filamentary bridges connecting them, all emerge naturally and inevitably when dark matter dominates gravitational dynamics. Yet even this invisible framework operates within a universe simultaneously being pulled apart by dark energy on the largest scales. Dark matter builds structure locally through gravity's attractive force. Dark energy stretches space globally through its repulsive influence. The universe exists in a constant dynamic tension between these two unseen forces, neither directly observable, but both absolutely fundamental. On relatively small scales up to galaxy cluster sizes, gravity wins the cosmic tug-of-war. Galaxies form and persist. Clusters grow more massive through mergers. Structure builds despite expansion. On the very largest scales beyond clusters, dark energy prevails inexorably, driving galaxies apart and pushing entire regions of space beyond our cosmic horizon into permanent invisibility. Let yourself float between these cosmic forces, perfectly balanced in the present moment. James Webb has shown us that the universe is not merely larger in physical extent than previously expected. It is more intricately organized, more deeply interconnected through invisible structure, and more fundamentally dependent on unseen forces than we ever imagined possible. What we see through our telescopes, the stars, galaxies, and glowing nebulae that fill our images, is only the illuminated surface of a far deeper and more complex structure beneath, an unseen architecture of dark matter and dark energy holding physical reality together while simultaneously pulling it apart. And when we step back far enough to consider that structure as a coherent whole, another profound realization becomes unavoidable in its implications. Even this vast, intricately interconnected universe is only what we can observe from our particular position in space and time at this moment. Beyond our observational bubble, the universe continues indefinitely, shaped by the same invisible forces, unfolding according to the same physical laws, evolving in ways we can never directly witness. Entire cosmic histories play out beyond the horizon, forever separated from our history by the expansion of space itself. And you drift peacefully through this incomprehensible immensity, a brief consciousness witnessing infinity from one small vantage point. Let yourself release into cosmic vastness, becoming one with the expanding universe. Your thoughts dissolving like morning mist. Your awareness expanding to embrace all existence and simultaneously contracting to the infinitesimal point of present awareness. The universe breathes through you. Ancient starlight flows through your consciousness, and you rest in perfect peace at the center of your own observable universe, a unique perspective that has never existed before and will never exist again in quite the same way. Sleep, now. The cosmos continues its eternal dance, and you are part of that dance, always have been, always will be, floating eternally in the space between what is known and what remains forever mysterious. Rest, drift, dissolve into stardust, become the universe observing itself, and sleep. The universe holds you gently, infinitely vast and infinitely intimate, and you are home.